It's like kind of weird. Like that's like
Right, there's a similar point in the class. What happens at change? Like some are like pretty clear because they change time. But we can change time by prompting, or we can change time by consumption. There are 2.4 items per job. One of them is in the domain, so this is question point, they want to. Use the mic.
I think I should be okay.
It's supposed to die.
Okay, this it should be okay. Thank you.
Said when they know that I say, yeah, bro. And I think also just like, like formal in there, or washers or some shit. Really just drink, really severe.
Alrighty, howdy, can everyone hear me? Howdy, hi, yes, okay, great. Welcome, welcome to your review session, sorry we're getting a couple minutes late. This time is yours, what questions do you have? This can be about quiz, final, anything from the semester. I just want to open the floor to y'all first.
What's the breakdown look like on the file, like questions from midterm 1 to?
It's pretty, I would say it's pretty even with the, I guess it's a little bit heavier on like the stuff that you haven't been tested on yet. So a lot of equilibrium, rate constants. I feel like those get asked a good amount. And then the other two are broken up for the rest. So I would say, it's pretty evenly spaced, but there is a lot of emphasis on the stuff that you haven't been tested on yet. And then it's about 25 multiple choice and about 6 to 7 short answer. So that's the breakdown of that. What else? 6 to 7. Yeah. Short answer. And the short answer, just like fill in the blank, circle a question. What class are you in? Ultimos, I don't have a copy of the mock exam because y'all don't get one yet. Altman does have a mock exam. That's on Canvas. Yeah. Yeah, absolutely.
Just do it.
Yeah, if you're in Altamos's class and you haven't done your survey, you should do that right now. Go ahead. What question? 2. This one here, use the thermodynamic. Yep. Okay. So for question 2, we have use the thermodynamic data below for water to complete the following sentence. When 5 kilojoules of heat has been added to 25 grams of ice at 10 degrees Celsius, the water is blank. So what they're asking for it here, or I guess how would you go about starting this question? Mm-hmm. Yep. Yep, so this is H fusion. This is okay. What else is important to know based off of the information we're given from this question? What is this point right here? What temperature are we at? That's at 0. What about this one up here? That's 100, right? We're in water. They told us that our melting point is 0 and then our boiling point is 100. Where are we starting on our graph? Basically the origin, right? We're at -10. We're under here, right? We're starting at -10. They're saying that 5 kilojoules of energy goes into this system. It goes into your ice cube at this point. So they want to know, okay, if you give it 5 kilojoules, where does it end up on our graph? Okay. So how can we break this up? What's the first thing we have to do?
If the change in temperature from -10 to
Yeah, perfect, right? So we have to get from -10 to 0. What equation do we use for that? Good. Q is equal to MC delta T. Do we know Q here? Kind of, but we're solving for Q. We need to figure out how much energy it takes to take our ice cube from -10 to 0 degrees Celsius. So do we know the mass of our ice cube? What is it? Good. So we have 25 grams. Do we know specific heat? It's the 2.1, right? We're still solid water here, so we need to use the lower specific heat. Bless you. What's our delta T? It's 10, right? We're doing final, which is 0 minus negative 10, which is going to be 10. So you have 10 degrees Celsius. So Q is equal to 527.5. What's the units here? Joules. Okay, so it says it takes us 527.5 joules of energy to get from negative 10 to 0. How much energy do we have? Does that use up all the energy that we put in? No, it doesn't, right? This only uses 4,472.5 kilojoules, or sorry, joules are left over. Right, so we still have 4,000 joules that we can, kilojoules that we can use in order to then now melt our ice cube. So what do we do now? Good, right? So we need to keep going, right? We still have more energy that we can use. So we're going to see how much energy it would take to melt our ice cube completely. How do we solve, what equation are we using for that one? So I want you to pay super close attention here to our units. So in our heat of fusion here, we're given kilojoules per gram. Okay, we're not given joules per mole, we're given kilojoules per gram. So do we need to change our mass that we're given? No, right? We're going to use the mass times the delta H of fusion. This is not Q. This is Q, excuse me. Okay, we don't need to change our 25 into moles. So you can say this is 25 grams times 0.334 kilojoules per gram. So we end up with 8.35 kilojoules. Can we fully melt our ice cube? No, right? We only have 4.4 kilojoules left over, but we need 8.3 in order to fully dissolve. So where are we in our graph? Right about the first flat line, about halfway. Right, somewhere around here. So what's going to be the answer for this question? It'll be B, right? At B on those flat lines, we have a mixture of both of our phases. We have a mixture of solid and liquid. Some of our solid still exists, but some of it is being melted. At the second top line, we have some that is liquid and we have some that is still gas, right? So you're in between of both of them. Does that help your question? Yeah, does that make sense how you do it? What other questions do we have on 2? Alrighty, what other questions do we have in general? Yep. Yep. Anything specific about it? Like the overall order? Yep. So when we determine rate order, where does rate order come from? Of what? The balance equation of what? Yeah. Good, right? It's the slow reaction or your rate limiting step. Right, your slow reaction determines your rate law. And in that balanced equation, you can write your rate law from there. So if you have Mm. Which one here is our rate limiting step? 2a plus b goes to c. So how would we write the rate law for 2a plus b goes to c? Close, that's equilibrium. This one we're looking for rate law.
A squared times B.
Right, so we have rate. You're missing one thing in there though. K, right? We need little k, a squared times b. Right, we take the coefficient and put that as an exponent. And in this case, we have a 2 in front of a, and we have a 1 in front of b. So we have a 2 that goes as our exponent for a, and a 1 that goes as our exponent for b. What is the rate order for a? It's 2. It's second order, right? This exponent here tells you what your rate order is. So with respect to a, this is second order. What is our rate order for b? First order. What is our overall rate law or rate order? Not entirely. Third. Why is it third order? You have to add both of the orders of anything that's in your rate law. So in this case, we have A and B. We have first and second order. So this becomes a third order overall reaction. So with respect to A, it's second order. With respect to B, it's first order. Overall, it's third order. What are your units on K? Given that it's time is seconds and concentration is it's 1/2. Is there anything else? You say times n. Anything else? M squared. Yep. Your units for rates are always going to be molarity over second, or concentration, right? Molarity over some time domain, right? It might be minutes, hours, something like that, but some sort of time domain. More often than not, it's going to be seconds. So you need to have an exponent on the bottom for molarity that cancels out so that you have molarity on top. So if you want to remember a little trick, your units for M would be M to the overall order minus 1. Right, so you would always put 1/2 times M to the overall order minus 1. So let's look back at our example that we just did. We had 1/2 times M, what's our overall order? Third, minus 1. So what does that equal? Does that match what we said up top? You want to prove to yourself why this is? We have if we plugged in units for molarity for concentration, we have rate is equal to K times M squared over M. And now we end up with M cubed. So K needs to cancel out M cubed in order to end up with rate equaling molarity over second. So if we had an overall rate law, actually, I'm gonna I said rate and what? All right, here's your rate law. What are your units on K? What's our exponent? 6. Beautiful. Right, we have 1, 2, 1, 3. This is overall 7th order. So if you plug in 7 minus 1, it'll be 6. Questions there? This one's just a lot of practice. Do you have any more questions about rate law or rate order? Yep. Hopefully that works. All right, so for this one, we have what is the rate law expression for the following experimental trials? We're given 3 trials, A and B, and we're given our rate. So what would be the outline for our rate law here? Right, we don't know what our exponent for A is, and we don't know what our exponent for Y is. So we have to find that out from our experimental trials. What are we looking for if we're trying to determine the order?
But one of them is so constant, the other one changes, like no single change.
Perfect, right? So we want to look for, if we're solving for A, we want to look where A is changing, but B is staying the same, because that means that whatever happens to A is, the rate is only dependent on what is changing with A. So what two trials are we going to look at for if we're going to solve for A? From 1 to 2, right? In this case, we have 0.1 going to 0.4 and 0.1 going to 0.1. So since B is staying the same, A is changing, that means that this change in rate is the only thing that's causing, or the change in A is the only thing that's causing the change in the rate. So you can do this if you're really good at them. You could just divide your numbers and then look for it that way. If you want to write it out in terms of your rate law, you would say you would have to write the rate law for both of your trials. So you could say the rate for 2, right? You're going to follow the same thing. Rate 2 is equal to K A B. And you're going to plug in the values from each of your trials. So in this case, we know the rates. I would suggest putting your higher number on top than your lower number. That just makes you work with whole numbers instead of decimals. So I'm going to put rate 2 over rate 1. Our concentration of A, we can get straight from our tables. We don't know what K is, so we can't plug that in. But we know our values for A and B. What happens now? Yeah, we can just simplify it. So what cancels out? Those cancel out, and your K's are going to cancel out. What do our rates reduce to? Yep. 4. And what is our concentrations reduced to? 4. Yep. So what does X equal here? X equals 1. So what is the order for A? First order. Okay. Then we can do the same thing for our B. What two trials are we looking at if we're looking for B? 2 and 3, right? In those cases, A is staying the same, but B is changing. Quickly, how does 0.1 go to 0.2? Sorry. This is times 2. What about 4.8 to 4.8? That's unchanged. So what is our reaction order for B? 0, right? We have no change in our rate based off of a change in concentration. So that's a 0 order reaction. Yeah. Yeah, I think it should be 2 to 3 because that and A is not changing with those. Yep. You could still do 1 to 3. It would just be a little bit trickier. You would have to plug in your exponent that you now know for it. Yeah.
So we think that the rate stays the same, but A is now 0.10 and 0.20. Is that just getting consistent?
I think so. Wait, say it again. Yep.
So like if A and or trial 1 and 2.
Yep.
the two changes to 0.20, is that change just gonna be, to R2 or like second order?
No, no, nope. So, right, in this case, right, if we're changing A from 0.1 to 0.2. Yep, so in this case, if we add a fourth order, or sorry. If we have another trial, well, this is 0.2, this is 0.1. What did happen to get from here to here? How did we double, or how did we multiply our concentration of A? By 2, right? This is x2. So if we know that it's first order reaction, that means that for everything that the concentration does, the same thing happens to the rate. So what would your rate be here? Yeah, this would be times 2, and this would be 2.4. Okay, it's still first order no matter what reaction you're looking at. Yep. Okay, so our overall rate law for this would be K times A. We don't need to include B because it's 0th order. If I asked you to solve for K, like a value for K, how would you solve that? Say it again. Yeah, right. So you could just plug in your values for A, right? We could use trial 3. We could say 4.8 times 10 to the third is equal to K times 0.40. And we can solve for K that way. So B, we said, right, if you look at trials 2 and 3, we're going to double our reaction. But what happens to our rate? It stays the same. So what order is that? 0th order. So if you plug a 0 in for your exponent, it just turns to 1. Yep. So you don't need to include it. Yep. Does that help? This? Okay.
So solving for K, it'll just be K, A over A, and then just, it can't just be one then? Or-
No, so you only need to plug in one trial if you're solving for K. So you would plug in, right, 0.4 we picked from trial 3, and then the rate, or 2 or 3, right? And then the rate from that same trial. So K here is K is 1.2 times 10 to the third. Oh, sorry. Right, K is 1.2 times 10 to the third. This was from trial 2 or 3. If you found trial 1, I'm sorry. Sorry, this is 10 to the fourth. Right, and then K here is also 1.2 times 10 to the fourth. Right, so it doesn't matter what trial you pick, you end up with the same K value. Yes. Yep, if B was a first order reaction, then you just plug in the value for B. You can multiply, right? And then you just become algebra, you're solving for your variable. What other questions? Yeah. In terms of entropy or in terms of like what we did today, like Le Chatelier's principle? Yeah. So right, if we have this reaction here, where A plus B goes to 2C plus D, all of them are in the gaseous phase. This is Le Chatelier's we're doing. right? If I'm going to increase my moles of A, which way is my reaction going to go? Forward towards our products, right? This goes this way. If you're a visual learner, I always like to show this. I think of this as like a valley and then everything else. So now my valley, or not my valley, my hill that I have. So now my hill needs to fall to the other side. I guess fall to the other side. I'm on the wrong side. It has to go this way in order to fill out the rest of that, make it even across the board again. Okay, what if I decrease A? Which way is my reaction going? It has to go back towards the reactants, right? We have to go back this way. So again, visual, this time I think of the valley. And so I have to create more stuff, create more reactants in order to fill that valley that I've created. Okay, so we have to go towards our reactants. What if I increase amount of neon gas in system? Why wouldn't it change at all? Good, right? So if we're adding an inert gas to our system or any of our noble gases, right, they're unreactive, then it will not have a change on our overall pressure of the system. There's also no neon in our system here too, right? So this only increases, so this is no change in equilibrium. The neon gas just increases the overall pressure of the system. It's not going to interact with anything. It's not going to, right, create a side reaction. It's just going to increase the pressure of the system. And therefore, everything in partial pressure will stay the same. It'll just reestablish the partial pressure back to the same equilibrium. So an inert gas will never change equilibrium. Only pressure. Only changes overall pressure. What if we increased the volume of our system? Right? If we're increasing the volume, we're trying to determine what happens to our reaction. Are we going to have more reactants? We're going to have more products. Why do we say more products? Yeah, perfect, right? So if you think about, you have, we'll call it a softball size of pressure of gas in your system from this reaction here. We have a certain amount of moles of everything, but this time we're going to blow it up to a basketball size. We now have that same number of moles that we started with, but they can fill up more space. So in order to create the same amount of pressure, we're going to favor the side with more reactant or with more moles of gas so that there's more particles that can create a higher pressure. So if we're increasing the volume, we want to go towards the side that has the more gaseous particles. And in this case, we have 3 moles of gas here and 2 moles of gas here. So we want to go towards the part with the higher moles of gas. And so for increasing volume, we're going towards products.
So will an increase in volume always go towards the side that has more number of moles?
Yes. Yep. So if we wrote it this way, where it was if we increase the volume of this reaction here, this new one, which way are we going? This time we're going towards the reactants.
Let's just say A was a solid instead of a gas.
Mhm.
And B had two coefficient, but it's still going towards the reactant.
Great question. So let's say we have 2A solid, that looks like a G, plus 2B gas. Right, now we have this reaction. how many moles of gas do we have on our reactant side? We have 2 moles of gas here. How about our product side? 3. So if we increase volume, which way are we going? Towards the products.
Happens when it's the same.
Then there's no change in equilibrium. Does that help your question? Yep. Yes. Because your A product or your A reactant here is solid. So we, if we're just talking about pressure and volume, we don't count that. Yep. So it's different from the one in blue, because in blue, they're both gas. Yep.
This big temperature.
Oh yeah, perfect. So if we talk about temperature, I guess temperature in terms of enthalpy of the reaction. What are our 2 conditions for enthalpies of reaction? Yes, yep. So we can have delta H less than 0. What is this called? This is exothermic. Is exothermic heat released or absorbed? This is good. And then we can have delta H greater than 0. What is this called? This is endothermic. And what happens here with heat? This is heat absorbed. So if we're talking about temperature and Le Chatelier's principle, I want you to think of an exothermic reaction in that heat that's released as just another product, right? That's something else that goes into your equation on the product side. For your endothermic, think of that as another reaction, right? You have to have that heat in order for the reaction to happen. So that has to be another reactant in your product, in your equation. So if we have is this an endothermic or exothermic reaction? This is endothermic. So we can take this 5 kilojoules and we can say it actually looks like heat plus A plus B goes to 2C plus D. Right? Now it acts as a reactant. So if temperature increases, what are we increasing? Our reactants or products? We're initially increasing our reactants. So which way is our equilibrium going to shift? It'll shift towards our products, right? We're increasing this portion here. So we're shifting towards products. What happens if we decrease temperature? Good, we're going to shift towards reactants. This is only for endothermic. It would be the opposite for exo, perfect. Right, so if we have exothermic, this now is going to act as a product. So if we increase our temperature, we're increasing our product side originally. So which way do we have to go? Which way does equilibrium shift? It'll go towards reactants. And if we're decreasing heat, we're going to go towards products. Does that answer your question about? Yep. So you would be given your delta H either in your question or you would be solving for it in your question. But if delta H is less than 0, then it's going to be negative. That's an exothermic reaction, heat's released. And then if it's delta H is positive, then it's an endothermic. It needs to be taken in. Yep.
So also work the same way where if it's like more moles of gas, it would be on the product side, it would be limit.
That doesn't always necessarily true.
I thought it was like pretty similar.
Not always, because we can have like endothermic reactions that are spontaneous, that increase entropy, increase disorder. So think about melting an ice cube. That requires energy, right? You need to put heat into it in order for the ice cube to melt, but you're increasing disorder because you're going from a solid to a liquid. So it's not always correlated like that. What other questions do we have? Yep.
Did you go over the ice tables?
Yep. Anything specific about them or just like how to solve one?
Just like we're kind of understanding what each part does. And represents.
Yep. Do you want to like do it through a problem or something? Yeah, I'll find one. All right, so for this question, we have calculate the equilibrium concentrations when the initial concentration of H2 and I2 are 0.2 molar and Kc for the reaction is 64. Alrighty, where are we going to start with this one? Yep, we need to start with the initial concentration. So I always like to write my ice table. So I'll write ICE, and then I'll write my reaction going across. So I have my tables set up. What are our initial concentrations? 0.2, and where does that go? Yep, so we have 0.2. Here's 0.2. What about I2 or HI? What does that get? That gets 0. So a lot of us here are just going to start jumping into what the change column is going to look like. But I want you to remember why we're doing the change column. At the initial concentrations, we're saying, are we at equilibrium? How do we check to see if we're at equilibrium? Products over reactants, but what letter are we solving for? Q, right? We're solving for Q. If we don't know if we're at equilibrium, We're questioning if we're at equilibrium, so we have to solve for Q. How is Q set up in terms of K? It's set up the exact same. So Q is going to be set up how? What goes on top? Product, so HI squared over H2 times I2. Now you're going to plug in your initial concentrations. We end up with 0 squared over 0.2 times 0.2. So Q is equal to 0. What does K have to be? Here's a lot. I hear a lot of like almost correct answers. It has to be positive, right? So it has to be greater than 0. It can't be equal to 0. So in this case, what is Q? Is Q greater than, less than, or equal to K? Q is less than K, right? If we don't have any products, Q is going to be less than K, right? We're given K too. We know that K is 64. 0 is less than 64. So which way are we going to go if Q is less than K? Towards our products, right? So we have to make change to make some products. What is our change line going to look like? What does H2 get under this change line? Minus X. What about I2? Minus X. What about HI? Plus 2X. So at equilibrium, we have 0.2 minus X, 0.2 minus X, and then 2X. How do we solve for equilibrium concentrations? We can put this back into the now K expression. And we end up with this here. And what is that equal to? Equal to 64. How do we solve for X now? We can multiply the denominator out, but what do we notice is happening in the denominator? Right? It's the same thing. So this actually is so we can actually take the square root of this whole one. And now we can multiply our denominator. Does this answer our question? No, not quite just yet, right? Our initial question asked, what are the equilibrium concentrations? So now we have to take that X that we just found and plug them into our equilibrium portion of our table. So we would have 0.2 minus 0.16. And don't forget about the 2x for HI. And this would be the answer to our question. Yeah. No, nope, it's all individual based off of the reaction. So, right, even if we had right, this was 0.2.200. This is a thing. Right, your change in X here. What's our change for 2A? Minus 2X. What about B? Minus X. What about C? Plus 3X. What about D? Plus 4X. Right? It's all dependent based off of the coefficient in front of that reactant or product. It's all about molar ratios. Does that answer your question? Does that help your ice tables? Yeah. There's some pretty good practice in the notes if you haven't done all of them yet too. They walk you through some various ones. But when you have to solve for equilibrium concentrations, that's about the hardest you'll have to get. The math might get a little harder depending on how they ask it. But setup is the same. Yep. What other questions? How do we feel about our final? What's up? Yep. Oh, great question. Great question. Okay, so we're going to look at question 23. So I'm going to give you a second to read it. All right, what volume in liters of CO2 gas at 645 torr and 800 Kelvin could be produced by the decomposition of 45 grams of calcium carbonate, excuse me, and you're given your R value. So you tell me, how would you solve this question? Yep, so, right, we know that we have to somehow get to using our gas constant. Yep, so we're first going to convert our calcium carbonate from grams to moles. She didn't give you the molar mass. That's kind of sad. I'll calculate it for you. It's 100.09 grams. Okay, so that gets us to moles of calcium carbonate. What are we looking for? We're looking for CO2. Is that a reactant or a product? That's a product. So how do we convert from reactants to products? It's a 1-to-1 molar ratio. Perfect. So we can get how many moles of carbon dioxide are produced from this reaction. We're now in moles. Does this answer our question? Nope. What do we have to do next? Now we can use PV is equal to nRT. We're given R, we're given pressure, we're given temperature, and we're looking for our volume. Can we plug in pressure directly? No, what do we have to do? Yep. So we have to take 645. Not 20. Okay, and now we can use PV is equal to nRT. We're looking for volume. We just found our moles. And I'm getting D, 34.8. Does that make sense how we work through that? Okay. Okay, so you tell me, how would you solve it? 24, when titrating 13.7 mils of 0.129 molar HCl at what volume of 0.135 molar sodium hydroxide do you expect to see the equivalence point?
Yeah.
Pretty close, yeah. Right, so in this case, we have two monoprotic acid bases. So if you were to write out your reaction, what are our two products here? Perfect. Right, so we have a balanced reaction. There's no like H2, there's no calcium hydroxide where you end up with two OHs. So this one is just a 1-to-1 molar ratio of the two. So in this case, it is just M1V1 equal to M2V2. Do you need to change your milliliters to liters? No, we don't have to. Right, so I'm going to take my molarity and my volume of my acid. That has to equal the molarity and volume of my base, because at the equivalence point, our moles of acid and base are equal. And I end up with 13.1 milliliters, so A. Now I want you to ask yourself, does this make sense? Does 13.1 milliliters make sense for your titration to reach the equivalence point?
Polarity's a little bit higher.
Perfect, right? So if you have a high volume, then you need a low molarity. And if you have a high molarity, you need a low volume, right? They need to be opposite of each other. And since our molarity for our sodium hydroxide is a little bit higher than our molarity for our acid, then we need to have less volume of that higher concentrated item in order to reach our equivalence point. Yes.
So if there was like two, multiply that. 30.
So it looks slightly different than that. So we could have HCl and strontium hydroxide. What would be your two products there? H2O, sorry, SR. SRCl. 2. Right, HCl, H is +1, Cl is -1. OH minus is -1, but we have 2 of those for strontium. So strontium has a +2 charge. That's why we need 2 chlorines in order to balance out the strontium charge. So what happens with our reaction now? Is it balanced? Yep, we need 2 HCl and 2 H2O. So now for every 2 moles of HCl, we need 1 mole of strontium hydroxide. So it's still going to be M1V1 equal to M2V2 here. But if you have a coefficient with acids and bases, you're going to take the reciprocal of the coefficient. So in this case, it would be, again, 0.129 molar, 13.7, and 0.135 times X. But the 2 from your HCl, you need to divide by. Because for every 2 moles, you need 1 mole of base. So you need to take that 2, divide it by 2 in order to get 1 to 1. And that doesn't matter if it's the acid or the base that's diprotic. It'll just divide by 2 both times. Yep. Say it again. 20? Okay. So for question 20, we have, what is the wavelength of light that is emitted when an excited electron in the hydrogen atom falls from n equals 5 to n equals 4, and the photon that is emitted has 4.88 times 10 to the negative 2 joules of energy? What equations do we know? I think we also get a formula sheet. You can't read that at all.
Oh, let's see this.
Yep. So in this case, the 2 that we're looking at is going to be C is equal to lambda frequency, and then energy is equal to H times frequency. So if we know that C is equal to lambda frequency, and then energy is equal to H frequency, what can we solve for? We can solve for lambda, right? We can use those two separate equations, or you can use the combined one, and you can say that energy is equal to HC divided by lambda. Because we just solved for frequency, plugged it in there. Do we know H? Yep. 6.636, 626 times 10 to the negative 34. I think that's what it is. Right? C is the speed of light, which is 3 times 10 to the 8th. Do we know lambda? Nope. And then do we know energy? Yes, it's given to us in our question. Okay. And then this just turns into solving for lambda. So I got 4.07 times 10 to the negative 6 meters. Yeah, that's just extra information. In a different question, they might ask you to solve for the energy of that photon. And that would be the energy is equal to H times 1 over N final minus 1 over N initial. I think it's something different, H something, but there's like the N final over N initial equation with the coefficient in front of here. And I think that's given to you. But that's how you would find the energy of that transition. She just gave it to you directly. Yep. So right now that's just extra information. Anything else that we want to go over today? We do have this room till 6:30. I do see another group standing outside, but I do have it until 6:30. Yeah. Say it again. 25? Yeah. So in this case, so for 25, you want to look at your solubility chart. And we're looking for things that will form a precipitation or a precipitate. So the solid formation. Just based off of, without looking at the solubility chart, NO3 will always be soluble. Right, so this is soluble. Sodium Na plus is always soluble. NH4 plus is always soluble. So I think magnesium, this magnesium carbonate, I think would be your precipitate right here based off of your solubility chart. But you just want to look at the ions and then if it's soluble or insoluble, and that's just given on your formula sheet with everything else. But in this case, you just want to switch your partners. So for magnesium, NO3, 2 plus K2CO3 You have to break this up into its two ions. So you'll have magnesium 2 plus and 2 NO3 minus. And then 2K plus and CO3 2 minus. And then you're going to switch your positives and your negatives. So magnesium is going to go to CO3 and potassium is going to go to NO3. So you'll have KNO3 and magnesium carbonate. And you just want to look to make sure that if you have the carbonate reaction or carbonate ion, that it would be insoluble with magnesium. And if it's insoluble, then it would be a solid, and then that would be your reaction. Does that make sense for the, yeah. I think so. Right, you're given your solubility chart, so we can check here. Yes, so here, CO3 2 minus is usually insoluble, except for when it's paired with these ions here. Magnesium is not one of the exceptions, which means that if anything is paired with that carbonate ion, it will be insoluble. It will form a solid precipitate, except if it's sodium, potassium, or ammonia. So in this case, magnesium carbonate would be your precipitate, so it would be A for that one. But that's your solubility chart that's given. Your periodic table, your various ions. These aren't really your strong acids, but just a couple constants there. And then your formula sheet. So I don't think you're given the strong acids and strong bases. But I think they would clarify for you. I don't think you're required to know them. But knowing your 6 strong acids is always just good. Any other questions? Feel better than how we started? Yeah, okay. So I guess we'll wrap it up for today. If no one has any other questions, I'll hang around a little bit in case someone just wants to ask me. I will have a Zoom review session Wednesday. I'm thinking 7 o'clock. Just so I can get home from work and everything. I will update you Wednesday morning on what time, or I guess Tuesday afternoon tomorrow, what time that is. And feel free to bring any questions you may have. Except if you're taking your quiz. If you ask me a quiz question, I'll be pissed. And I wish you the best of luck. Thanks for coming this semester. It's been a pleasure.
I need to leave.